Very good evening to all. Today we have a very important session, which is construction of push down automata. Right? In case if you are watching this video, please let me know. I'll be waiting for your comments. Yep. Please let me know, guys, if video and audio is clear to you. Please put in the chat box. I hope it's very clear to you. Yeah, I'm waiting for your comment, guys. Good evening to all. Very good evening. Is the session live? Okay. In previous two videos that in the previous two lectures, what we have covered is context-free grammar and what is a push-down automata, basics of push-down automata, right? Yeah. Guys, put in the chat box if any issue with the audio and video. If it is everything clear, please let me know, guys. Okay. Yeah, I'm waiting for the replies. If you are live, please let me know. Everything is fine. Come on. I can't see any comment so far. Why is that happening? Can I proceed with the class? I believe that you are able to see this video. In case if you have any issue, please put in the comment box. Yeah. So in the previous session, what we have covered is what is a PDA, right? PDA basics we have covered, like configuration and how many parameters are there, right? how to perform the different transitions like push, pop or no operation, how to read the input or how to not read the input. So we have seen all the cases yesterday in previous session. Now I'll be covering construction of the PDA, and mostly this topic you can ignore while practicing, but you should aware, at least you should have 1 or 2 times practice. As you know, it takes time. In the exam there you cannot see construction of the PDA questions, but if you can do, you can easily understand what is CFL, what is DCFL, what is the difference between them. Now in this session I'll be focusing on purely construction. Okay, construction of PDA. This is only the main target today session. We will see lot of constructions today, as many as possible. Construction of PDA. Let's begin with the first machine. We already know this problem, right? The first problem, a power n, b power n, we did it, but still I want to start afresh. Okay, yesterday's second and third problem I'll be covering today, but today is the completely from basics, again beginning. So in this, first take any enough length string so that you will understand the logic. Okay, 4 bits, and my assumption is always clear, like I'll take the epsilon at the end or I'll take the dollar at the end, that is your choice, only to terminate or to accept the string. Now initially, you know, on this stack what do you have? Z0, and when you read A, that is the first combination is A comma Z0. That's why in the machine what we did is, from initial state a self loop A comma Z0. What is the meaning of A comma Z0? A is the input, Z0 is the top of the stack. What you want to do you want to pop or push or skip? I want to push, because I want to remember this A's, right? I want to push all of them as it is. But at this time they here push A's, and from here to here we do pop A's. But how? How many A's you want to push? How many A's you want to pop? Here I am pushing 1A and I am popping 1A, because I want to cancel 1A, 1B. If there are 100 A's, I want to cancel 100 B's. Okay, I want to compare them. So A comma Z0, I am going to push, so A Z0, A Z0. But here when I push A onto the stack, the next symbol, if I want to read A, but A comma A is not going to take the help of this transition. If you talk about A comma A, input is A only, but top of the stack is not Z0 now. That means this transition, even though you kept the self loop, but it does only once for this machine. Why? Because next A cannot see the Z0 on the top of the stack. What it sees? A. For that you have to take another self loop, or you can write here itself, A comma A slash double A. Now what happens? This A comma A, you push one more A, and next time this A comma A is going to help, because the second symbol onwards every A is going to see only A on the top of the stack. Only the first A is seeing the Z0. So this transition will be for the first A, and this transition for remaining A's. Now these 4 A's will be pushed onto the stack one by one. Okay, so this transition will help to push 3 A's, and the first one will help for 1 A. So 4 A's are pushed, but when the B comes first time, B comma A, so what you do? You can't stay in Q0, because if you stay in Q0, again A's might be coming here later, you don't understand the sequence. So to understand the after A's B's, we will go to another state. B is the input, but A should be top of the stack. We do pop, that A will be deleted, as to mention epsilon means A is deleted. So you go to Q1. So this B is going to pop A, and this B is going to pop A, and for that once you go to Q1 on B also same job, B comma A, you pop it. We did that. So go, and this one don't go to anyone, just stay there itself, right? You can stay there itself. This one you can stay here itself. B comma A epsilon. So here B comma A pop, B comma A pop. But when dollar comes, or epsilon, you can also assume epsilon Z0 comes, then you should say accept, go to final. How you do that? So from Q1 here, when dollar comes or epsilon comes, Z0 should be top of the stack, keep Z0 and stay in final. But this will accept at least 1A, should be there. At least 1A, 1B should be there. But if you don't have anybody, n is equal 0, epsilon from Q0, directly you will see $Z0 if nobody is there. Okay. Then finally, it will be accepting because you are halting at final. Okay, you cannot come to the final in the middle of the reading. So only at the end you should come to the final. In case any time if you read epsilon, if you keep instead of $epsilon, right, you can come here also, you can come here also. But if you come in the middle, the remaining string can't read from the final state because you don't have the transitions from the final state. I hope this motion we did in the previous session. Just I want to repeat. So I hope this is clear to you. Yeah, I can't see any comment. Please put in the comment box, guys. You know, I have to wait for your comment. If I can't see the comment, then it's very difficult, right? So please help me. Put something in the comment box. Okay, let's start with the second question. Now the question sequence changes, right? Now I don't want to keep the same problem. So let's start with some other problem. Second. Okay, let's start with a power n, b power 2n such that n greater than or equal to 0. Anyhow, we don't say this is a regular, right? It's non-regular because we have a dependency. What is the logic now? Let's take 4 a's. How many b's should be there? 8 b's. 1, 2, 3, 4, 5, 6, 7, 8. And end of the input you may assume epsilon or dollar is your choice. So this is what you do. You push double a's. Push 8 a's. Push double. That means every a you have to put 2 a's on the stack. Now what do you do? Push double a's but pop the same number of a's that you see the b's. Don't pop double a's here now. Push double because 4 a's will become 8 a's and now 8 a's can compare with 8 b's, so that equalness will happen. That means a's is twice to the, half of the number of b's. Here b's is twice to the a's, but a's is half of the number of b's we have. So to do this, what we do? Initially we have a Z0 and every a comma Z0, what do you do? Same, Q0, a comma Z0, a comma Z0. How many a's you want to push? 2 a's. So how do you write? Double a Z0. See, Z0 is there and 2 a's extra there. So first a we push 2 a's. Okay, first a we push 2 a's. Next this a comma a, top of the stack is a. Now this will not work. So what do you write? A comma a, and this 1 a already there. How many a's you want to push? 2 a's. Total 3 a's you have to see if I am picking this a. So this a I am going to push 2 a's. Now this transition can help us. Every a will push 2 a's, right? Every a it will push 2 a's. Now we have 8 a's. When the b comes, b has to pop 2 a's. So how you do that? 1b you should pop 2 a's. Can we do directly? If you want to design PDA, you can. But deterministic PDA, it cannot pop 2 a's at a time. So what you have to do, you can also do one way. Every 2 bits you can pop 1 a. When you push all the a's exactly same, there is a logic 2. So logic 1, you can only design a PDA, you can't design deterministic. But this language is DCFL, deterministic language, so you must have a DPDA. So DPDA will design another way. Now what you do, every b I want to pop 1 a. How I do? B double a slash epsilon. But this double a you cannot write in deterministic. Why? Here if you remember, sigma cross gamma is there, not a gamma star. So here you can keep only 1 a if you want, right? So this deterministic transition should not appear like this. Anyhow I am designing PDA, so I have no issue. So 1b I pop 2a, every b I pop 2 a's. 2 a's, done. So this b also will pop 2 a's and this b, oh what I am doing? Why I am doing 2 a's popping? I am very sorry for that. It's a b's are not twice, right? So this logic is going wrong. What was our assumption? This is completely wrong assumption, right? I am thinking somewhere else. No, we went somewhere bad situation. What was our logic? It's not popping 2 a's. What was our logic? Logic is important. Pop exactly same a's. But when you want to pop 2 a's, then b you need to pop 2 a's. But right now we don't need it because b's are not half of the a's. If b's are half of the a's, then you could do that. So logic is very clear. every A push 2 A's, every B pop 1 A. So how do you do that? Every B pop 1 A. That's it. We went to some other bad situation, but that's wrong, right? Every B just pop 1 A. 1B, 1A only. Then only it will match exactly. So you should have the clear cut how many A's you are pushing, how many A's you are popping. If you are pushing 2 A's, then no need to pop 2 A's. Why? Because here number of B's are twice the A's. That is the reason every A we push 2 A's, but while popping 1B, 1A only. Right? We are not matching equal number of B's and A's. What we are doing, B should be twice to the A's. Then to do that, what we need to do, every B we pop 1A, but while pushing only we'll do the double. So that this number of A's in the stack will be equal to number of B's in the input. Look at that, what happened. Number of A's in the stack will be equal to number of B's in the input. That's why it's a matching will become so easy for us, right? Because while pushing only we have taken care how many B's are there, how many B's should be there. So end of the input occur, this is the end of the input. When end occurs, then judge not only the target. So if this is number of B's is twice the number of A's, at the end what happens? $Z0, you can go to final. Now the question is, if epsilon is there, is it epsilon valid here? Yes. So from Q0 you can see dollar directly. So you can, this is to accept epsilon. Okay. Now you should understand, once you know the first problem, then all the problems look so easy. Only the thing is why we are designing this way only. Now this is deterministic. Earlier I was wrong because I was popping 2 A's. Now this is deterministic. You can see sigma gamma, sigma gamma, sigma gamma, sigma gamma, sigma gamma. It's matching everywhere, right? So sigma grass gamma. I did not take anywhere more than one symbol on the stack, right? Other side is gamma star, that will match everything. Is there any other logic you have here? This is the deterministic motion, no doubt. And do you have any other logic? Yes. What is other logic? This is push exactly same. You can do that as homework if you really want it. Like I have 4 A's. This is another logic. You can try on your own. But what you have to do that time? On this stack, you push same number of A's. 4 A's are there. 4 A's you push one by one. But here, 2 B's you pop 1 A. 2 B's you pop 1 A. 2 B's you pop 1 A. How you should do that? Every 2 B's, how can I pop 1 A? You can't write 2 B's at a time. But how you do that? What you do, first B you skip, other B you pop. First B you don't touch the stack, means don't look at the stack, don't pop anything. Whatever the stack symbol is there, keep the same. If A is there, A keep as it is. So now what you do is, first B skip, B comma A keep A, don't delete A. But next B comma A epsilon. So next, put a cycle from here. Let's say you come here and take the help of somebody here, right? Take one more state, extra state, and first B skip, other B you pop, and put a loop here. So this state will decide every time. So every 2 B's it will pop 1 A. Okay. So first 2 B's you stay here, and every 2 B's you should come back. Every 2 B's you should come back. So take another logic here. This is a logic 2. You work on if you can understand. And logic 1 I designed. Okay. You can explore. There are infinite ways to design the machine for the same language. Remember that? How many ways? Infinite ways. I am only doing one way. Why PDA is so important? Because we are thinking now in general, logically, what is possible, what is not possible. And somebody asked, can you write a program for prime logic? In the world, there are n number of logics, not 1, 2. But definition is going to match with everyone. Okay. The same way here, all these machines, this logic or this logic, you design a machine that is going to accept the same, even though machine looks different. Okay. So I have given homework for the logic 2. You can try that later. Now next problem. Third. A power 2n, B power n such that n greater than or equal to 0. If n greater than or equal 1 is there, then don't accept epsilon. From Q0 don't read dollar. Okay. Now what is it? A's twice means, let's say I have 6 A's. Then how many B's should be there? 3 B's. Then how do you proceed? This time what you can do, every A you push 1 A, but every 1 B you pop 2 A's, that I did earlier, right? That's the one logic. Second logic is every 2 A's push 1 A, So that on this stack, first time you will see 1A for 2A's and other 2A's 1A, other 2A's 1A, then every B you pop 1A. Every B you pop 1A. At the end, you should see, at the end of the input, you see Z0 only. Correct? So this is how you can design. But how I do every 2A's 1A push? I should read 2A's, but I should push only 1A. How do I do that? First A, you should not push anything. Means just read, skip, don't do any operation. And this A push 1A. That means every 2A's you push 1A only. What I did? First A, I don't touch the stack. Whatever it is there, I'll keep the same. But next A, I'm going to push. Every 2A's I do the same procedure. So every 2A's I push 1A, 1A, 1A. If there are 100 A's, I will have 50 A's on the stack. So that 50 B's will come and pop all the A's. Now let's try on the try to design a machine. Q0. How I do? I'll take care of the one state. The state will help me. 1A I skip, other A I push. So there are 2 A's I am going to read from Q0. First A skip, second A push. First A. So A comma Z0. So what I do? I keep the same. That means I don't push A. Now this time A comma Z0. So I push it. But this is only for the first 2 A's. Next 2 A's you don't see the Z0 because this A came now. First A came, right? This A came here. Now what happening? Now next time A comma A comes because A already there on the stack. So keep the A, don't push now. But next second A, that's a fourth A indirectly. So every 2 A's we are going to push 1A. So here we are going to push 1A, double A. So push, skip, skip A, push A. So every 2 A's we are pushing 1A. And when the B comes, your logic changes. Every B pop 1A. Every B you pop 1A. Now this will take care of the equal, not equal. The number of A's is twice the number of B's, right? Now you see the stack. In the stack you have 3 A's. In the input also 3 B's you have. Fine. Now if it matches, this 3 A's that 3 B's matches, then when the dollar comes, end comes, dollar epsilon, then Z0 should be there. If this Z0 is there, means this all the A's are matched with all the B's. Okay. Go to final. But here epsilon is there or not, special case is there. So from Q0 also directly dollar can come and Z0 can be on the top of the stack to accept the epsilon. So this is epsilon path, and if you push the A's, then B should come to pop. And this is also similar machine that we did in the previous two. 1, 2, 3 looks same. Push for A's and pop for the B's, because A's and B's you have to compare. A's and B's you have to compare. Let's see some logics now. Okay, before starting the fourth problem, right? Fourth, fifth, you just think about it. Fourth, A power M, B power N, such that M is greater than N. Okay. Fifth is, think about these problems now. M less than N. Sixth, A power M, B power N, such that M greater than, or let's try with first not equal to, M not equal to N. Seventh, A power M, B power N, such that M greater than or equal to N. So all these problems are similar. Only the thing is you should understand what is the condition that you are looking for. Okay. Fine. So fourth one, M greater than N. I'll just explain the strings, then I explain the logics one by one. M greater than N. First, what is the value of M and N in all of them? Greater than or equal to 0. I'm not mentioned at anything. So greater than or equal to 0. So now here understand the symbols. A's, number of A's greater than number of B's. Here number of A's less than number of B's. This way you think about, because M and N you will forget who is M, who is N. But understand here A's greater than B's. So what is the string that I can take? Let's take a big enough string. So more A's, let's say few B's, and definitely more A's than B's. Don't say half of the A's or of twice the A's. Don't say that way. So more A's than B's. 1B, 100 A's also correct. Here 100 A's are there, followed by 1B is also correct. Now how you do this? What is the logic for this? In the stack, you push all of them, right? You keep all of them in the stack. Like you keep all of them in the stack. Z0 is there somehow here. Now, how many B's are there? 4 B's. So 4 A's will be popped because you have this many B's. At the end, when dollar comes, who is there in the stack? Not a Z0. Who is there? It is A, dollar comma A, which means when end of the input occurs, the stack has some A's. Stack has some A's. It means A's are more, that's why A's left on the stack. So this is how you do dollar comma A. This combination is for acceptance. Okay, dollar comma A. Now keep the A or pop, it doesn't matter. Just dollar comma A will go to final. Okay, you can perform any operation now in this sequence. So this is the acceptance condition. Okay, that's about A's more than B's. What about A's less than B's? Now you see this one. 2 A's are there. There are so many B's are there, let's say. Now, this A's you push onto the stack. Z0 is there, okay, here. Z0 is there, don't worry. Here Z0 is there on the stack. A push, but B you pop A. Now this B comma Z0 don't accept now because so many symbols left. You did not complete the input. So many people I saw that B comma Z0 go to final. Wrong, because this might be A. The string is invalid. Will be invalid if you have A here. So you need to check every input symbol till the end comes. So what you do is ensure these are only B's. We know that B's are more. Ensure only B's are there. So B comma Z0, skip. When dollar comes, dollar comma Z0. So here you skip everything, then go to accept. Okay, there's a dollar comma Z0, but before that B comma Z0 is your target. B comma Z0, keep a Z0. So all the B's, the remaining B's in the input, you just skip all the B's. When dollar comes, dollar comma Z0, go to final. So there are two things you have to take care. You can't go when you see the B comma Z0, you can't go to the final because input is not yet over. So you have to decide only at the end of the input. Okay, the condition is very clear, B's are happening more, but you are not sure only B's are there at the end. So this is a logic you should take care. We'll design. Okay, next one, M not equal to N means M greater than N or M less than N. So you know how to design this. Just combine the transitions of both. So this means M greater than N or M less than N. We will see that how to combine these two. M greater than or equal to N means M greater than N, that means this one, or M equal to N. We did already M equal to N, right? This one, M less than N or M equal to N. Can we do it very quickly? Yes, we should do that. Okay, it should not take much time. Okay. Sorry guys, I'm not able to see the chart. I don't know what happened, but let me do the fourth one. Okay, fourth one greater than A power M. Logics I have explained. I'm just following what I have explained. Now I have taken, let's say, more A's, less B's. Okay, let's say dollar is at the end. What is our logic? Same logic, that A comma Z0. We are designing deterministic only. Remember that all machines, all languages are deterministic here. A comma A. So there is no change. You just push all of them as it is onto the stack. How many A's are there? 1, 2, 3, 4, 5. All of them you push one by one. And when B comes, you pop A. Same logic. When B comes, just pop A. Doesn't matter how many are there. Just do the same job. But later, if more A's are there, then definitely B's will be less. Then B's are going to pop only few A's. Then end of the input, still it's seeing A on the top of the stack. It means dollar comma A will be the acceptance condition from here. From here, if you see dollar, that's end of the input, but A is on the top of the stack, then either you pop or push or skip, doesn't matter at all, right? Because you are not going to touch the stack later, you are going to final now. End of the input, you don't see what is there on the stack now. So now you go to final. Is there any special string here? That is also should take care. Who is greater? A's. Without B's, A's can happen, because when B power 0, A's can be any except epsilon. So here you should do at least one more A's can happen, like more A's, only A's are coming, after that no B. Because if you see only A's are there, it means A power 3, B power 0. That means A power m, B power n, m greater than n is happening. That means without B's also string is valid. Only A's string is valid. So if A's you push, and after the A's, if dollar comes, you should go to final. But dollar comes, how do you know that A's are more? Dollar comma A means only A's happened, I'm going to final. But here A's and B's both happened, but still A's are more, you're going to final. So this path is very important. This path is very important. When you don't need it, if they restrict that at least one A, one B is coming, like m comma n greater than or equal to 1, then you don't need this. Here greater than or equal to 0, that's why this is needed, only A's is valid. Without B's, it is valid. Okay, so here m comma n greater than or equal to 0, even though both are greater than or equal to 0, you can't take both are 0. Why? Because m is greater than n can be 0, this can be 0, but this can't be 0. Both cannot be equal. Okay, done. Very, very simple machines. Okay. Fifth one. Now number of B's more. A power m, B power n, m less than n. Now B's more. How you do B's more? 2A's, so many B's are there. How you guarantee they are only B's? Okay, you keep on the stack 2A's and 2 B's, you pop 2A's, but from here to here you need to read, right? Just look at B comma Z naught only, you should guarantee that only B's are there. Skip all the B's. From here to here, skip all B's, skip all B's. Okay, you need to skip all the B's, and dollar comma Z naught, you just go to final. Dollar comma Z naught, just go to final. So how you do that? From Q naught, every A push. So you can write two ways. In the previous session also I explained. You want to push all the A's, directly you can write A comma epsilon. But you want to do deterministic, you need to specify A comma Z naught, A comma A. Otherwise one transition you can write, no need to write two transitions here. Now B comma A pop. See, so many machines we have the same concept. Here there is no change, right? From year to year every time same, because after A's, B's is coming. That's why we are doing this way. Now see, when the third B comes, B comma Z naught. From here the B comma Z naught, what you have to do? You need to skip. Don't change anything on the stack, keep the same, but you read the B, and that you continue for all the B's. Every B you read it, but keep the Z naught, because if you delete the Z naught, then the other symbol cannot see anything on the stack. Now after that, when the dollar comes, you just go to final, But any special input here? Here who is more? B is more. There is only B is valid or not? Without A, because now A power 0, B power 1. Now B power is greater than A power. So single B, double B, triple B, these are very special, right? They are also valid. In previous language A's are valid, here B's, only B's are valid. So how do you accept only B's here? See that only B's are there. B comma Z naught is a starting symbol condition. Here B on the top of the stack Z naught. So here B comma A covered, A comma Z naught, A comma A, but B comma Z naught is not covered. But if B comes, only B's will be there, no A. So only B's, how do you guarantee? This is already doing only B's. So from Q naught, if you see B comma Z naught, if you see B comma Z naught, then come to here, read every B and go to final. That's what we are doing here, right? So this is a very special, already we have a state, just you should know that only B's are coming, come this path and read every B and go to final. But you are not using the stack at all, because you are not pushing anything when B comes. Okay, directly B is coming from initial state, then take this path. I hope this motion is perfectly alright for m greater than n, m less than n. Now the question is, Sir, how do I accept that sixth one, m not equal to n? See, already greater than n is there, right? Here you can add extra transitions for m less than n. How you do that? See, you already know that sixth nothing but a power m b power n such that m not equal to n. It means this is m less than n or m greater than n. So you design any machine, just combine other transitions, very simple. Which one you want to do, which one is very easy? Let's say m greater than n. More a's than b's. How do you design? State names you no need to keep, not required. A z naught, more a's, right? So do as it is that you do for a power n b power n, that you do for a power n b power n. Now b comes pop 1a, every b pop 1a. This logic is same for all problems that we are doing so far. A's push, b's poppy. Now more a's means here dollar comes, then a will be there. So from here, if dollar comes, a is there on the stack, then go to final. Not only from here, only a's are there. When dollar comes, go to final. This one is going to accept a's more than b's. A's more than b's. So this one is accepted. Now b's more than a's. For that, just add the transitions. If b is more than a's, what happens here? After this, b comma z naught may happen. So more b's might be left on the input. So read all of them. After that, dollar z naught may come. Then come to the final. If only b's are there without the a's, then directly from here you go to this state, b comma z naught, z naught. So directly b's are coming, skip all of them, come to final. So that yellow transitions are for m less than n, and this white transition, this especially this path and this path. Okay, this path and this path is for m greater than n, m greater than more a's. This is a dollar comma a, dollar comma a. Fine. So now all the combinations are required in this language is covered. Okay. Only the thing is you should know what a symbol need to be compared. What is input, what is the top of the stack. Right? Take enough length example and work out, you will be getting the whole logic easily. Done? Now you just try homework, that 7 and 8. Can you do that yourself? 7 and 8, just you do homework. Okay. That is a power m b power n such that I didn't remember, just remember m greater than n, one. Another one is m less than n. Okay, just take care. Assume it is homework. Very simple. What you do, m greater than n machine you design, equal to conditions you keep there. Equal means when both are equal, dollar comma z naught should be there from the q1 state. Here also m less than n machine already we know. Take that, just in this, if a's and b's are equal, what will happen? So just take care of this too. Fine. So let's move to the different case. Ninth one. See, in these problems, w belongs to a comma b whole star. Number of a's of w is equal number of b's of w. See, all these problems are same what I am doing here. Okay, do not assume they are different. They almost, except one transition, almost they are same. But what is the difference now compared to the previous problems? There also we are checking equal, greater than, less than, but here also we are doing it. What is the difference? There also we are checking a is equal to b, a is greater than b, a is less than b, but there a power b power, but this is not a power b power, any string in the world, any string in the world over a comma b. Okay, all these problems are so easy. Not equal also possible, but you don't have much effort. The first you design this, one transition you change, you will get another problem. You will get a machine for another problem. So can you try this? How many are there? 1, 2, 3, 4, 5, 6. Okay. First work on logic, don't design it. If you don't know the logic, you can't design it at all. You will go wrong. First, what is the logic for these problems? How can you compare A's and B's? Can you try? Okay, first we will take 9 only. First we will take 9, but remaining all just same. Whatever I do now, W belongs to A comma B whole star, and number of A's of W is equal to number of B's of W. So tell me how you compare this A's and B's. You don't know which sequence happens. See, what is the difference between this and this? A power n, B power n. Here only A's followed by B's, but here there is no such thing. Here only like epsilon, AB, double A, double B, these strings are valid. But here epsilon is valid, AB is valid, BA is valid, double A, double B is valid. What else? A, B, AB is valid. Equal number of A's and B's. 2 A's, 2 B's. Any order they can come. AB, BA is valid. What else? BA is valid. BAAB is valid. BB, like this, all where you have equal number of A's and B's, they are valid. So understand the difference. Here A's you push, B's you pop, but here you can't say which one you will push. First A might come, B might come, the order is not decided, right? Because W can be any string in the world. So what will you do now? The question is very simple. If the stack, see on the stack who is there? If Z0 is there, that means there is no A, no B. Now input, if A comes, push it. B comes, push it. Because nobody there on the stack. You have to remember something now. So if A comes, push. Even B comes, push. In both the choices you have to push. When A comma Z0, A comma Z0 combination is coming, you have to push. B comma Z0 combination, you have to push. Why you have to push? Because nobody there on the stack. So this is one scenario. When do you require the symbol A to be pushed or B to be pushed? Okay, when nobody there on the stack, nobody means no A, no B left on the stack. You have to push. But now there is another situation comes. Suppose A is on the input, already on the stack A is there. Of course, on stack you can't see both A and B at a time, any instance. Why? If A's are pushed, only A's will push, B's we don't push there. Okay, if A comma A situation comes, or B is there, now B is coming. Now what do? Will you pop it or push it? How do you know that? See, we are doing cancelling A and B only, right? We don't cancel A with A. So when A's are already in the stack, A is coming, you have to remember it because more A's are coming. You need to increase the count. So what you do is, you will push it. A comma A, this combination you will push. And always worry about what is input, what is top of the stack. Okay, don't confuse about operation. Operation is decided based on this only. Okay, B comma B comes. What do? You will push. So now two situations we know push. When nobody there on the stack, push. When the same symbol is there on the stack like input, push. When opposite symbols are there, when A is here, when B is here, then pop. Or when B is here and A is there, pop it. So pop situation, the pop case, the case, which case is the next case? Let's say the case 1, case 2. Okay. In both the situations you do, right? The case 3. What is the case 3? Input is A, but top of the stack you see the B. These opposite symbols, that A is the input, B is the top of the stack. You just pop it. What is another situation you may have? B is the input, but top of the stack is A. Top of the stack is A. So B comma A, pop it. Okay. So we have these situations, and at the end of the input, when dollar comes, nobody should be there. That means equal A's and B's happened. Okay. So remember these situations. Now work on any input, you will understand what's happening. Okay. So I'll just take one case, A, B, 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 A, B, A, A. So is it valid input? Because 4 B's are there somewhere and 4 A's are there. So it should be valid. So what is our target? If end reaches then stack should have only Z0. That means A's and B's are equal. If in case when you reach end but stack left with A's, means A's more. If the stack left with B's, B's more. That's why this problem is so easy for the remaining problems. If A's more, A's will left on the stack, B's more, B's will left on the stack. Not equal means either A's left or B's left on the stack. So depends on the condition, you are going to look at the stack at the end. You are going to look at the stack at the end. Okay, now I hope you got a clarity, right? So what we are going to look at. So now Z0. A Z0, this case. What do you do? Push. So I am going to push this. So I have A now. Now B comma A, what do you do? This case. B A, opposite symbol, pop it. So B is going to pop A. B is going to pop A. So this B will pop A. Next B comes, but who is there in the stack? Z0 now. Nobody there, only Z0 is there. So B Z0, first case. First case, this is the first case, right? This push. So here we will push. So B I am pushing here. Now B comma B is which case? This second case. Same symbols are there in the input and top of the stack. So push this B also. We are pushing this B also. Okay, push. Now A comma B, opposite symbols, you pop it. And B comma B. So now we need to push because B, B are both same symbols, right? B we are pushing. A, B, pop. A, B, pop. When end happens, when end of the input, so who is there in the stack? Z0 means the number of A's equal to number of B's. It's a very, very simple. Only you should know there's three cases when there nobody there, push. Same symbol in the input and top of the stack, push. Different symbols are there in the input and top of the stack in different input symbols. Okay, don't worry about Z0. Don't assume Z0 and A, this is coming on the third case. No, third case and first case are different. First case is if Z0 is in the stack means nobody there. This might happen in any point of time during this, right? Not only in the first symbol, but later also you have seen Z0. This B comma Z0, we pushed it, right? That can happen whenever something comma Z0 is happening, means before this equal number of A's and B's happened. That's why stack left with only Z0. Whenever equal number of A's and B's are happening till that point of time, then stack you will see Z0 only. Okay. For this, what is the motion? What is the motion? Very simple. Can I do here? Yeah, you can design. This position is enough, right? I'm designing here. You can see Q0. What are the combinations you have? All of them you write it one by one. A Z0, push. B Z0, push. A comma A, same symbol, push. B comma B, same symbol, push. And A comma B, not same, pop. B comma A, pop. So all these sequence symbols, all these combinations are going to take care of equal number of A's and B's. But if it happens, equal number of A's and B's happens, what do you see here? $Z0. Then go to final. Go to final. That's it. So this is the motion for this problem. And the same motion for every problem. Only this transition only changes. This combination never changes for all these problems, right? So now look at the 10th one. How easy that problem is. What is the 10th one? Number of A's of W greater than. It means there is no change in the motion. See that all the combination that you write you should keep for everyone. Push for nobody there. When A comes or B comes and Z0 is there, you push it. And same symbols are coming like on the top of the stack what you have, then push it. Opposite symbol is there in the input and top of the stack, then pop it. Because we are cancelling those. Now here this transition only deferred. When do you go final? Now who is more? A is more. Then who will left on the stack? A left. So when end of the input occurs, A is left on the stack. That's it. Okay, operation you decide. This is not going to be an issue. You can do the push, pop, no operation because already you are going to the final. Now after that nothing is there because end of the input occurred. So when the end of the input occurred, A should be on the top of the stack. That's all the condition, and operation you decide. Really this does not matter. Okay, but this sequence is very important. Done. If b is more, just you write dollar comma b. Getting not equal if you want, dollar comma a might happen, or dollar comma b. So two transitions you have to write here. You may come with the dollar comma a, or you may come with the dollar comma b. So other problem. So now remaining all I can take in a sequence, right? 11, number of a's less than number of b's. What is the machine? So you can design here itself. The machine is, same as the previous problem, right? Right, all the, how many transitions you have here? 1, 2, 3, 4, 5, 6. So keep this 6 transitions for everyone. Keep 6 transitions as it is. 6 transitions, keep as it is. Only change is here. What is the change? Dollar comma b slash b. Go to final. That is same as the previous machines, transitions. No change in that 6. Okay, next 12th. Number of a's of w greater than or equal to number of b's of w. Right, machine is again same, right? You have to keep the same 6 transitions here. Here what do you write to go final? Now greater or equal. Greater means who is greater? A's is greater. So what you have here? First one is dollar comma a. That's fine. If this is not, what is other combination? Or equal. So equal number of a's and b's might happen. For that what do you write? Dollar comma z naught. So one is to cover the equal, other is to cover greater more a's than b's. That's all you have. Machine is same. Okay, 13. Did I miss the number? 14 we had, right, total. Sometimes I miss the transitions, sorry, number 14. Not equal is missing. Greater, sorry, this 12th is actually not equal, okay. The 12th is not equal. What I took here is 12th is this one. So this is actually 13th, okay, 13, and this is 14. This is 14. Okay, the 12th will take care later. Number of a's of w less than or equal to number of b's. Now what do you do? Same 6 here. But this one to go final, who is more? B is more. So who is more? B is more. Dollar b slash b. Other possibility equal. Equal means dollar comma same edge, because there are 2 transitions here. One is to cover equal, other is to cover the more b's. That's all we have. And the 12th one, that's we missed, right? 12th. Okay, you can design here. 12th is just we can also try if you really want not equal to. Not equal means either a is more or b is more. So keep all the same 6 here. And now dollar comma a will cover more a's, dollar comma b will cover more b's. That's all. Very, very simple, right? So these 14 languages, are the beginning to our PDA construction. Okay, now I'll give just 2 minutes. It's a break for me, but it's a thinking process for you. 15th. Okay, the w hash w power r such that w belongs to a comma b whole star. So you have anything here, right? You have any sequence, doesn't matter, but hash exactly reverse will come here. This b will come here, and this a will come here, this b will come here, this a will come here, same symbol will come there, but that's in the reverse manner. Okay. So if this is a w and this has to be its reverse. So how you do that? Think about it and see how many of you can design. It's a very famous problem. It's a deterministic context free language. So far all the languages that we have designed, right, they are DCFLs. Yeah. Try to design your own PDA. Let's see how you proceed for the construction. So take time, 2 minutes, 1 minute. Very simple, right? What do you have here? You know, all of them put as it is on the stack, right? Z0 is there below. Keep everything onto the stack as it is. Push everyone. When the ash comes, skip it. But know that then reverse will begin. So B cancel it, A cancel it. So you need to match now onwards. Okay? B comes, B should be there. A comes, A should be there. If not there, that's not definitely in this form. Okay? So some kind of palindrome concept, this one. So every match should be there. Okay, sorry. When end of the input happens, who is there on the top of the stack? Z0, because these all are getting cancelled because they are going to match. So there you will accept. So designing is so easy. How you design? So you take a Q0 support to read entire W. The entire W, how can you read? Everything, every combination you should push except ash. So till the ash, every combination, A might be beginning symbol, B might be, doesn't matter. Like A comma Z0, push. If the first symbol is B, push. We don't care till the ash. Suppose A is there, now A is coming, A is on the stack, A is coming, then push. Suppose A is coming but B is there on the stack, push it. Suppose B is coming, A is on the stack, push it. B is coming, B is on the stack, push it. So everything you do the just push operation. Now when you change the mind, that reverse of the begin happens when the ash is an input appeared, doesn't matter top of the stack. Top of the stack might be, this whole W could be epsilon because W also belongs to epsilon. So this might be epsilon, this might be epsilon, means only ash is also valid input here. So if when ash comes, Z0 may be on the stack, doesn't matter, or A might be on the top of the stack, or B might be, so keep the same. Or ash comma B might happen, keep same, no change, don't change the stack. We will start comparing from here onwards. B, A, will compare that way. So after that from Q1 matching should happen. Like if B is an input, then top of the stack should be B. If A is an input, top of the stack should be A. And what happens to B comma A comma B? That never happens in the valid string. In valid string may happen. If A comma B happens from here, then you don't have a path, means they will go to dead state by definition. So now if this is a W, this will match with the reverse of the string, then at the end what happens? When dollar comes, end comes, then top of the stack should be only with the Z0. That means the entire the sequence is popped this W. Then you go to final. Okay, minimum string is ash. Is it accepted? Ensure that hash comma z naught, you will come here, then dollar comma z naught, you will accept it. Yes, epsilon string will be accepted. Epsilon not epsilon, hash will be accepted. Okay, epsilon is not a valid string here. Hash is a minimum. Minimum string is hash. Next, a hash a. Next, b hash b. Next, double a hash double a. Next, a b hash b a. It's reverse, and so on. All such strings are valid. Okay. Is there any better PDA? This is a deterministic motion, right? That's why it's looking lengthy. Is there any better simple PDA for this? Yes, we have. Look at that. Another PDA I'm designing. How simple looks like. See. Right? There's a method one using deterministic transitions. I don't need to use deterministic. I can use non-deterministic. See how easy? Q naught. Why do you want to write every combination? Either A or B you want to push, right? Just do one thing. A, anything is there, push. B, anything is there, push. These two are enough to take care of all this, right? 6 combinations you can just take care of with the 2 combinations. Okay. Now, hash, anything is there above, just you have to take care, right? So what you do is hash epsilon slash epsilon means I just change my mind, change the state when hash comes, but no need to tell z naught, d naught, a, b, b. It's going to cover every combination here. Okay, Q1. Now, this one you can't avoid. You have to keep because they are deterministic and you need to carefully look at who is top of the stack. So, here b comma b pop, a comma a pop. And when do you accept it? That you know dollar comma z naught. See, this motion is so simple, right? Compared to the first one. Here you need to write you need to write every combination. Here you just write few non-deterministic combinations because these are not allowed in deterministic. Why? Because you can't look at the top of the stack epsilon, right? You have to look at some symbol. You have to look at some symbol on the stack. Here you have to look at some symbol. That's why it's deterministic. Here you are not looking at stack. You are throwing A, you are throwing B without looking. That's non-deterministic. Okay. That's why sigma cross gamma star we have written in the domain side. But here in deterministic, sigma cross gamma, that maps to, you know, sigma star. That's this side. Okay, this is about a W hash W power R. Done? So many ways, but you should think in right way to design this one. Yeah, please note down. Okay, now I am going to give some problems. So you need to think about the logics. For the exam point of view, you no need to design. You should know for this language, do you have deterministic PDA or not? If deterministic PDA is there, we call it as DCFL. If it is not there, but still PDA is there, then you can call CFL but not DCFL. So that is the logic we have to build. For that, it will take a little bit more time. Okay. Same, right? Can you think what you have to do? Just think. This say what you do. Don't push. Skip. This W push. This hash skip. This one pop, but with a match. Okay. Think about how to do it. You know all of them, right? Just I am going to design. A Z naught. Skip. This is a skip operation. Skip A. That's the first symbol. Next, W you want. You know already just W's you have seen, right? All of them. A comma Z naught, A comma A comma B, B comma Z naught, B comma A, and what else? B comma B. So you just do the push. Six transitions. Order is doesn't matter because all are independent self loops. W done, push, this is a W. What is it called as? W. This whole thing is W. So this is A. A, W, and hash should come now. What should be on the top of the stack? Here, A we are not pushing, right? So we have no restriction what is there. So Z0 may happen. What else? R. So you can also put here if you want a bracket, but I am just writing individually. Okay, Z0 slash Z0. You know, in all of this, all of them also you can write some other way as either A, but when A comes, A should be there. Z0 comes, Z0 should be there. B comes, B should be there. You can also put like this. Now this is the symbol hash. What is this? Hash. A, W, hash. Now the reverse. What is the reverse logic? Match. A comma A, pop. B comma B, pop. This is going to ensure the reverse of the string will happen. Whatever it is pushed here, and its reverse should appear here, right? Finally, when the end happens, only stack should have Z0. Then go to final. Okay. So this kind of logic is needed. For the exam point of view, how do you know this is a deterministic? You need to understand the sequence of operations without having any confusion. Yeah. I hope you are able to do it right. Let's go for one more, a different case. This is different. B. How do you do that now? So again, think logically. W you have to push, no other way. Hash, skip. Reverse, you need to pop, but with a match. Then this B definitely happens, but when will happen? B, when it comes on this stack, you will see Z0 and keep it, but the next has to be end. So you are going to skip this, but with a combination B comma Z0, you should not see any other combination apart from this. B comma A, B comma B, this should not happen because there is only one should left at the end. So this one you need to guarantee. So how you do that? First W, right? You know W how to push it. So I'll just write with a few combinations, but I'm designing a PDA, but you also know there is a DPDA. Instead of writing all the 6 combinations, I'm just closing with the 2 combinations. Now hash comes, skip. You also have the shortcut for this, right? Epsilon slash epsilon. Now reverse, you have to mention A comma A, pop. B comma B combination, pop the symbol. Next, when you keep on doing it, at the end, after some time, suddenly you will see B comma Z0. Of course, you can't take this path because this path will work only for B comma B. When the stack has B, then only you can get the input B here. But this one, when input is B, but the stack has no symbol, at that time, it might be ending with the B because this remaining is done. So now you will go to, this is very important. After this B, you should see the end definitely. That's a $, or epsilon. Then go to final. Now you see what you see in the combination, like your string form exactly the machine form also, right? This is your W, this is your hash, this is your reverse of the string comparison, and then this is your symbol B you are reading, and that's end of the input, right? End of the input. At the end of the input, only Z0 left. Fine. Okay, let's look at some different languages. 18. See this, A power n, B power n, C power m, and for simplicity I am writing nm greater than or equal 1. Of course, greater than or equal 0 also you can take, but so many extra strings will come, like if 0 is there, then only C star accepted, or only A's and B's are accepted. So this many combinations were there. If you have greater than or equal 1, then all of them are present, at least one A, at least one B, at least one C, but A's and B's equal and C's no comparison. Now what is your logic? I want you to think about the logic, not a machine. If you are not able to design the machine, it's okay for the exam. I told you in the yesterday class also, previous class also, we don't need construction of PDA. We need how the people constructs the PDA. That is important. Now what is the logic? A's, what you do? B's, what you do? C's, what you do? This is needed to understand. Now the dependencies between A and B, right? How you do it? This dependency. A's you push, but how many? That you should understand. Every 1A push 1A, that you should know. And for B's, what you do? Your push A's you will do. For B's, pop A's, but how many A's you will pop? 1A. Because every A I am pushing 1A, so every B I should pop 1A. In case every A you push 2 A's, every B also you need to pop 2 A's, because you need to match exact count, same count. C's, what you do? It's at the end, right? You skip or push, but you can't pop anyhow because nobody left on the stack. You can either skip or you can push, because anyhow you don't want it. So you can skip, that is a famous choice, but you can also push this C's onto the stack, because at the end I am going to accept anyhow, because I know now there is nothing to compare, but only C's are coming. I will ignore them and I will go to final. Or I may push it, because you don't want it. When you don't want it, either you can keep it or you can throw it. That's a choice. This is one logic. Other logic is push C's. That's it. Now how do you design the machine? C? Q naught. How you push A's? You know that. How? A comma Z naught, A Z naught, A comma A slash W. So this will guarantee push all the A's. But how will you know at least 1A happens? That is decided by what you do here. Are you doing C or B here? B comma A. This will guarantee when the B comes, at least 1A already there on the stack. It means A's were happened. Okay, so this will guarantee 1B is happening and 1A also happened. So what you do? Every B pop 1A, right? Every B pop 1A. How long? How long? Till you see the B's, A should be there on the stack. Once C comes, how do you know that there is no A left, or how do you know these two are equal? That C will decide. How? C comma Z naught means A's and B's are equal. If I say C comma A, means A's are more, because if A is more, A's will left on the stack. So this combination is going to decide basically whether these two are equal or not. C comma G naught, it means these two are equal. How many A's are pushed? That many A's we popped. That's why when C came, nobody left on the stack and all the B's we scanned. Now we go here, we just read every C. This will guarantee at least one C happened, and read every C, and at the end of the input, end means maybe assume dollar or hash, whatever the condition that is given to you. Go to final. So this is how you do it. A power n, B power n, this machine is same all the time. First problem, and C comes, Z naught should come, because at least one C should be there. So skip every C and go to final. Done. But if the same problem I ask for greater than or equal 0, so many extra comes. I'll show that too. Okay, see here. If I change this problem little bit, okay, that problem I already kept it, duplicated the slide. So now let's say it's a greater than or equal 0. How many special things are going to come? See here. Now only A power n, B power n, accepted. Only epsilon, accepted. Now only C's, that C star, accepted. Now all together is covered here. A, B, C, everybody is there. A power n, B power n, C plus, where n greater than or equal 1. This is covered already here. This is only covered here, right? Now only epsilon not covered. Only A's and B's not covered. So epsilon is anyhow covered here. Here also covered, right? So now this combination should be taken care. How? Epsilon, how do you accept? From Q naught, you need to go final when dollar comma Z naught comes. This is to accept epsilon. Now A's followed by B's without C is also valid. So here dollar comma Z naught means A's and B's are equal, but no C is coming. Then go to final. Now this one is done. Only C's you have to accept. From here directly C's may come. How you do that? So that C's, any number of C's can come here and accept. So to go there, if only C's are coming, go there, C comma Z naught, keep Z naught and read every C and go final. So this extra combinations are going to come, but remember, when you are able to do greater than or equal 1, greater than or equal 0, also able to do it easily. Okay, but special combinations will cover. That's the 19th question. That's why we always do greater than or equal 1 to make it simplicity. Done? Okay. So don't worry about the greater than or equal 0 now onwards. A power n, or let me write A power m, B power n, C power k. Previously we did m equal n, m comma n comma k greater than or equal 1. Now condition is, let's do m is equal to k. It means what? It means which is equal to A power n, B power, let's say something else, I, C power n, such that n comma I greater than or equal to 1. Right? A's and C's are equal now. Previously A and B are equal. So how you do it now? So think about how you do it. So now this A's you push, but this B's don't do push, because you need to skip now, only one option, because B's are not dependent on anyone. C is what you do, pop A's, because you need to compare these two, correct? Can you do it on your own? Yeah. Can you try it? Tomorrow we are going to talk about only languages, because we need to identify a lot of languages. So we will work on many languages tomorrow. But today we need to understand a construction. Okay, languages we have a very special session tomorrow. Today focus on construction. A's, what you do? Push. So same, how you push it? A comma Z naught, A comma A. So this will take care of all the A's pushed. Now when B comes, you just need to do. We know that all of them are going to appear anytime. So here B comma Z naught never happens, because at least one A is there. Okay. So B comma A. So skip. How you skip? B only. Sorry, A only, right? A only we keep on the stack. We don't pop it. So now this Q1 should guarantee all the B's are skipped. Now see, A's are there. We know, don't touch. A's are, we are seeing A, we are keeping A only. We are not popping it. We are not pushing it. Now all the B's we skip with this transitions. Now when C comes from Q1, C comma A we are going to compare. So pop it. So every C we pop 1A. Every C we pop 1A. So we compare C with A's, in between B's comes, then we just ignore the B's, and once the C's and A's exactly equal, so what you do? At the end Z naught will come. See, we are only doing for equal. In the exam they may ask A is greater than C's, A is less than C's, A is equal to C's, A is not equal to C's, A is greater than or equal to C's, A is less than or equal to C's. All can be done. The first 12 or first 9 models we did, right? First 9 problems. There all the answers are there. If it is equal, then C comma A, after that here dollar comma Z naught is coming. If suppose A's are more, then dollar comma A. If C's are more, then C comma Z naught comes, skip the C's and then go to final. So everything depends on the same first 10 problems only. First 10 problems, if you do well, then in all of them you can make 10 problems. I am doing only equal, you can do not equal, you can do less than, greater than, all of them, you know. That's what you need to understand. I might be designing only one, But this 20 problem, only 20, you can make maybe more problems. Like equal you convert to less than, greater than, less than or equal, greater than or equal, not equal, all problems. Okay. And one more I am doing for greater than or equal 1, you can do for greater than or equal 0, problems will be double. So maybe we have done 20 so far, but this 20 is equal to maybe 40, 50, 100, you don't know, right, until I write. So don't assume that we are designing few problems. No, we are actually designing a lot, but doing very few to understand all. Tomorrow we'll expand all this to understand the same 20 problems will represent lot. Okay. So equal to, not equal, less than, greater than, you try if you really want it. No need, right? Equal you are able to do, not equal also you can do it. Fine. Okay. 21. A power m, b power n, c power k, such that now b is equal to 6, that is n is equal to k. So what you are going to do, this is you take a decision, it's a first, right, either you push or skip will not impact. So mostly we choose skip this is, so that this b is we can push directly. This is we pop the same b's that we have pushed, because this we need to match. Okay. So can we construct the machine directly now? Initially what you have to do, definitely A's should happen, that is guaranteed, right? If not, then you don't understand. So here don't put a self loop of A comma Z naught, you don't understand. So what you do is at least one A should happen. For that we need to change the state to understand at least one A happened. If you put a self loop now, so B comma Z naught will not understand A is happened or not. So this will guarantee at least one A happened. Now you are skipping any number of A's. Now this B, no need to worry about the A's, because without A's B is impossible. But if you don't have this state, right, if this is the initial, now when B comes, we don't know whether A happened or not. Whether A happened or not, this transition only taken. But now without A, this B never happens, because initial is here. B comma Z naught, now we need to push B Z naught. But do you have, can you put a self loop here? If you put a self loop, what happens when B comes? Can I put a self loop that you should think about? If you put a self loop, will it work or not? Just think B comma Z naught slash B Z naught, right? When B comes, then nobody, A's will not come later, because A comma Z naught will not be seen next. So even you can put a self loop if you want it. But only for understanding, I am going to other state, but you can also put here still after A only B will happen. Then this B comma B double B. So these two transitions you can put here itself. It will work. It will work, because once B is pushed, only B's will be there on the top of the stack, only B can come, because we are not looking for A comma B at all. Now after that, C's, B's we are going to compare. When C comes, B has to be on the top of the stack. If all are in proper sequence, then at the end Z naught will happen, then go to final. Very simple. Skip A's. You can write that word if you are confusing sometimes. Skip A, but you remembered one A happened. This is also skip A. This is push B. This is also push B, but input on top of the stack sequence is changed. This one is pop B, because for a C we are popping B. This is also pop B. How many pop B's happened? That's exactly equal to how many pushes are there. That is the reason the dollar comma did not happen to go to the final. If it is not going to the final, means the string is invalid, right? Correct? Yeah. So now we'll go for very special problems, right? So far whatever we have done, this 21, all are deterministic languages, deterministic context free languages. If you want to write somewhere after this note, previous all 21, of course tomorrow we'll see many. Can you remember that? All 21 problems. So far all 21 languages that we have seen in the previous slide. deterministic CFLs. So no doubt they are CFLs also, but what we are going to see next, they are not called as DCFLs, they are called as CFL which is not DCFL. Okay, 22. Tomorrow we'll see lot. Today only beginning. Okay, these problems are very special and very famous. I'll write list of the problems, why they are very special to us. A power m, b power n, c power k, such that, let me write m comma n, k greater than or equal 1, comma, m is equal to n or m is equal to k. I just write equal here, but in the exam, whether it is here equal, not equal, less than, greater than, greater than, greater than, anything could come. This problem is similar. Okay, remember that I only take one because already we are seeing varieties, and if the same problem I do again and again, we are wasting our time. So tomorrow these extensions are going to come. First understand this problem, extensions tomorrow will write. Okay, any other very interesting problems we are going to write now. A power n, b power n, union a power n, b power 2n. Of course, you can write as a single language also. How you write a single language? This is simply you can write a power I, b power j, where j is equal to I or j is twice to the number of a's. The number of b's, if you look at, either equal or twice to the a's. So that you can write in simple single language form. When I write a union, don't assume two different languages. There are actually two different forms in the same language. Okay, it's a one language, but we have two types of strings. A power n, b power n, c, union a power n, b power 2n, d. Still it is not having DPDA, but this c, if it is there here, and this d, if it is there here, then this language will become DCFL. So here variations are there. I did not explain, but tomorrow these extensions will come again. So these four languages are very famous for us now, but a little bit variation that makes sense, that here I am writing those variations. 26, in case if you put a c before b, whether you have d or not doesn't matter, which will impact a power n, b power 2n, without c also fine. When c comes, we know b's are going to equal to a's. With directly b comes, then b's are twice the a's. This is basically DCFL. You can design a DPDA, and c you can also keep in advance. So these concepts we'll discuss tomorrow anyhow, but just think about these two languages for understanding. But what I want in these problems, all these four problems, my focus is only on these four. These four are CFLs. They are not deterministic languages. They don't have DPDA, but these problems are special, variations of the 25, 26, 27. Okay, but they have DPDA. These both are DCFLs, but these are not DCFLs. They are only context-free languages because they have PDA, but they don't have DPDA. Here PDA exists, but DPDA not exist. No DPDA for them. So that's one of the important concept. Now, if DPDA not exist, then how they can have a PDA? That's very important. Okay, and designing PDA is not important. Understanding why they have the PDA, that is important, because in the exam nobody will ask you design a PDA, design a DPDA. They will ask you, is it a CFL or not? Even they may not ask DCFL. They will ask mainly on, do you have a CFL or do you have a PDA or not? That's it. Is it called CFL or not? That's all you require for the exam. That's why tomorrow class is very, very important. Even though whether you are comfortable in construction of the PDA or not, you should know how to identify the language. Okay. 22. So now look at the problem 22. What is it? W power r. W power r. You know, it's a waste of time even designing and thinking about this problem, but it is worth if you understand it is CFL but not DCFL. For some people, they don't understand the PDA at all, because designing PDA is just, you know, non-deterministic, like non-deterministic finite automata. We have non-deterministic PDA now. Now we have a PDA for this, but there is no DPDA. We can construct PDA. But no DPDA exists for this, no deterministic PDA for this language. That's why we don't call it as DCFL at all. Okay. Now how you do that? Grammar, you know, grammar is very simple. You have seen that, right? A S A or B S B or A or B or epsilon. So this is a context free grammar for this language, no doubt, right? Every context free language, they have a context free grammar. But the problem is, what is a push down automata? We don't have any deterministic for PDA. Why we don't have? Because see this problem, when you have W power r, right? It's a very clear, this ash is the symbol which separates the push and pop operations. Here till here you push everything, but after that you pop by match. That's very clear. But when you don't have this ash here, then when do you start that push pop operations? That no clarity at all. Got my point? But if there is any string which is in this form, suppose if you see this string, right, this is the W, this is the W power r. Deterministically you can't understand this problem, but non-deterministically what you may do, you know, all of them you push onto the stack, but I don't know, I will try here, I will try here, I will try here, I will try here. There is at least one path which can go to the final. So this path, I'll push this all into the stack, and this I will match. When everything is, you know, matches, at the end not only left on the stack, then we'll go to final. So that kind of, you know, logic works. Non-deterministically you can find a path that goes to final, but which path goes to final, that you need to show. Machine will never show now, because not a machine is not a deterministic. Okay, machine has, you know, multiple paths for the same string, might be possible. Now you need to find a path which goes to final. So now what is my logic? W, I take a decision for the push. How you do that? Anything comes, I care, push, that's it. I care as just a push. How long? I don't know. I push nothing, or I push one symbol, or I push two symbols, I push. But after some time I change my mind. See that? I don't read, I don't look at stack, I don't do anything, but I change my mind. Maybe I change my mind at this point of time, maybe, I don't know, but if the string is valid, definitely at least one path that goes to final, right? So here I change my mind, then whatever I pushed, I'm going to pop in the reverse order. See that here, if really W power r begins, then this should happen. If really these two are matching, then at the end of the string, of course dollar or epsilon, then go to final. See this, I designed a PDA, but which is not a DPDA. I did not choose DPDA transition. You see that? Epsilon, epsilon. I don't know when to pop, when to start pop. So I just change the state. I don't know. If I change here, I will fail, because the remaining portion is not the reverse of this one. So I don't have a path to the final. If I change my mind here, then this string is not a reverse of this one, I'll fail. If I change my mind here, then this string is exactly reverse of this, then I will go to final. So any string that you take in this form, definitely it will reach final with at least one path. That path you will find somewhere here like this. Remaining path may not go final, but at least one path. But now how difficult is, I'm not able to say clearly when will you take this path. I need to look at, you know, the place somewhere. Why this always succeeds? Because it's a non-deterministic machine. No need to tell exactly which path, just show that there is a path. If you give me a string, definitely you can find manually, but machine will not tell you which path. You need to tell, because you design non-deterministic. Okay, it's just like, writing algorithm rather than the program. Algorithms no need to tell how the system executes, right? Program definitely executes and runs and produces an output, but algorithms no need to. The same way how algorithm works theoretically you write, same way this machine also says it is accepting the WW power R. Now there are various machines for the same language. If you really want to try deterministic machine, let's see how it works. WW power R, why we are failing to design a DPDA, now you will understand. See, when W power R begins, how do you know that? There is slight logic, when this is the present input, right? This is the present, and previous input, let's say this one. Whenever you have this situation, right? Previous input, then there is a chance at this point of time, there is a chance of beginning of W power R. Why? If this symbol same as the previous symbol, if both are different, reverse never. See, W and W power R, the first symbol of reverse should be same as last symbol of W. Both should be A or both should be B. That is the reason the reverse might happen, may not happen. If happens, then you will go to final. If not happens, there will be other path that can go to final. So either this situation may happen or BB. If this is the present input, this is the previous input, then again there is a chance. Only at this point of time there is a chance of reverse of the W begin. Okay, so using this combination you can try. If I take a string, of course we are wasting our time to understand this problem. Okay, not required at all. If you do it, see, you can try at this point of time the reverse might begin, but if you look at BB matching A, oh, it's not matching, so it's not. You may try here because the present is same as the previous, but if you try here, then this is not same as this one, and you can try here because present is same as the previous, but now look at this A matching, this B matching, this B matching, this B A matching, right? So here will succeed, here will succeed. So you need to try, but this is not deterministic. Here if we fail, again we are trying here. Non-deterministic means out of so many paths, at least one path will go to final. So how you design the machine? Like this. The problem why we don't have a DPDA, you can see now. A Z naught, no problem, we push. If B comes first, we push. If there are different symbols, A is here, B is on the top of the stack, we don't have any problem, we'll push. B comma A will push. But the problem happens if we have A is present, B is the present input, previous is also B. Then where is the previous one? On the top of the stack. So here the problem happens. Now you see, when A comma A happens, we should take the two choices. Either we may continue W, then push, or we may start reverse. There is another situation, B comma B. We may continue W or we may start reverse. But once the reverse starts, we will have only pops, nothing else. So only for this situation we have the non-determinism. That's why see, A comma A, we did not take one transition, we have taken two transitions, either this path or this path. If it is this path, we'll continue W. If this path, reverse begins. But we don't know reverse begins or not. That's why we take non-deterministic. One of the path will lead to success if the string is valid. Okay, and at the end, dollar comma Z naught will go to final. Really, you want to accept epsilon, so dollar comma Z naught should come this path also. To accept only epsilon. Okay. So that's why if you don't have a deterministic PDA, the very different logics present to design a PDA. So this is also PDA, how you can clearly understand A comma A, there are two transitions. But if you look at back, no such things. We have simply taken non-deterministic transition. They're not for deterministic. We never do deterministic like this, deterministic like this. We see, in place of epsilons, we always take somebody to understand who is coming. So that's why deterministic motions are very easy to understand, because everything you put an effort to design. Later on, everything is easy to take the path. But non-deterministic transitions, should I take this one or this one, you should understand, right? Machine will never tell you. Machine will tell you only one thing: I have a path, at least one path that goes to final, but you find out why did you design this. That's it. Okay, so that's why WW power R is a very famous language where you don't have a PDA. Why we don't call this a DPDA, even though every transition looks like DPDA? But see, from this stage, same input, same top of the stack, like sigma cross gamma, sigma cross gamma, like x comma y, this is x, this is a y, same xy, x is same, y is same x here and same y here. You have two different transitions. That's why you have 2 power q cross gamma star in a non-deterministic PDA. So the 2 power, because you don't know how many transitions you are going to take, that creates non-determinism. But in deterministic, we have this 2 power, we don't have. We have only q cross gamma star. That's why the difference comes. Fine. This is not called as a DPDA. It is PDA, which is not a DPDA, which is a PDA. Okay, which is non-deterministic PDA. You can see that from here, that x comma y somebody is pushing, and other x comma y you are popping. This might be going to the same state, it might be going to q0 only, this might be going to q1. That creates non-determinism, right? Here this no need to be same. Unfortunately, previous example we have same a comma a, but these two can be different. But same x, same input, same top of the stack, you are doing two different operations, you are going to two different states. That is why, this was the self loop there, and you are going to somebody else. This is not going to come under deterministic. It's a purely non-determinism, Okay, 22, right? 23. So now 23 is number of A's equal to number of B's, number of A's equal to number of C's. Okay, I only compared with A's and B's, but tomorrow I'll compare with B's and C's, B's and A's, C's and B's, C's and A's. So you can take any fixed symbol with other two symbols. Okay, tomorrow we'll see variations. 23. Can you try 23? 23. A power m, B power n, C power k. Why we don't have a DPDA for this? M is equal to n or m is equal to k. What is the meaning of this? It means A power n, B plus C power n, n greater than or equal to, first m equal n, right? First we'll take this, B power n, C plus, that is for m equal to n, R means union. Now m equal to k, that's A power n, B plus C power n, where n greater than or equal to 1. M is equal to k, covered by this one. M equal to n is covered by this one. Okay, either A's and B's are equal, or A's and C's are equal, but both are not different languages, both are in the same language. Some strings are having A's, B's equal, some strings are having A's, C's equal. Now the question is, suppose I have A's, now B, I don't show remaining at all. Okay, now this A's anyhow you will push. Okay, that's good. This B, what will you do? Will you push or will you pop? See, now this one says every B pop 1 A, but this one says don't pop A because C will compare with A. So now I am in dilemma. Should I ensure M is equal to N condition or M is equal to K condition? If M is equal to N, every B I will pop 1 A. If M equal to K, I will skip all the B's, then every C I will pop A. So I don't understand, every C I should pop A or every B I should pop A. So now here the confusion happens, so deterministically not possible. So B, you have to take two different paths to cover these two conditions. Okay, now let's see how to cover it. This path says that push A, pop A, skip C. This one, push A, skip B, pop C. Same sequence will pop A, sorry. Push A, skip B, pop A. Will follow that sequence. Q naught. First what you do, push A's. How you do push A's? You know how to do it? A comma anything, just push A. Z naught or A might come as the top of the stack. Instead of two transitions, I just took one. Now B comes. B comma A only comes, but I don't know what to do. My string could be this one, because future I never know it, because when I am pointing here, I only know about the past that I have pushed onto the stack. Now for this B, I have to take the decision. Is the B is equal to S or C is equal to S? We don't know. So one thing to cover the M equal to N, another one is to cover that C is equal to S. So this one I am going to cover M equal to N. This path I am going to take care of M equal to N. This path I am going to cover M equal to K. So how you do it now? If M equal to N, every B I pop A, right? So this one, every B we pop A. Every B we pop A. Then when a C comes, we just see these two are equal, then C comma Z naught will happen. When C comma Z naught means all the A's are popped by the B's. Then keep the Z naught and every C, you just skip, then dollar comes, go to final. That will take care of this strings, and all the strings you want to cover, then go this path. B comma A, just keep A only, don't touch A. Keep the A but skip the B's. All the B's you skip first, because we don't know how many B's will come. Skip the B's, don't touch the A's. A's will be the same, and when the C comes, they start popping A's. All the C's will pop A's. When both C's and A's are equal, at the end Z naught only appears because A's and C's are equal. So all the C's that comes, the A's popped, then at the end we will go to final. So this is the machine. Now you see why non-determinism happening. They see that same combination, we have two different paths, two different transitions. This B comma A, you are taking two different choices, never happens in deterministic machines, right? In DFA, we only have the input, but in a DPDA, we have input as well as top of the stack. So both you have to look at. If this is B comma A, this is B comma Z naught, it's a deterministic only. But here B comma A, here also B comma A, that's why this is not going to be deterministic. That's why you don't have a DPDA, no DPDA for this. What we have? We have only PDA. That PDA is this way. Clear? So now after looking at this problem, right, can you try the we have 10 minutes. Can you try other two problems? Tomorrow I'll be only discussing the languages, so many languages, maybe I don't know how many, 50, 100, but these two, take it as homework. I'll help you now only. I will help you now only how to design. See here, A's, what you do? Push, blindly push. Same A's you push. But look at this one. If equal, then every B you need to pop one A. If B is twice the A's, then every two B's you need to pop one A. What do you do? For this B's, you have two choices, either equal or twice the A's. So every B, so B comma A comes, then pop in this path. This path, every two B's you need to pop one A. Means first B skip, second B you pop A. So every two B's in this path, every two B's pop one A. In this, every here also B comma A combination, what will you get? Every B pop one A, every one B. Every one B pop one A. So there are two different choices. So this path only you should guarantee every one B pop one A. This path, every two B's you pop one A. So both should not combine, both are different. You know both of them how to design, right? Individually we design both the machines. Now both of them we should make in the single machine, but that is a non-deterministic choice. Now this one, see, actually they are different strings but in the same language. What you do? A's push, but when B's comes, this B or this B we don't know, right? B's comes, one path to have equal, other path you have the twice. But if you see the equal, at the end guarantee C comes. If you see every 2 b's pop 1A, at the end guarantee D comes, then dollar comes. That's all. The same machine, only at the end, instead of dollar Z naught, you just go for C Z naught, then after C dollar Z naught. Here at the end dollar Z naught was there. Now you take D Z naught, then dollar Z naught you should get, because you have extra symbols. If I delete this 2, then only you will have this 2, right? So I hope you can do this too. You try this. In case if you don't get, please ask me tomorrow. So please try this 2 homework, and tomorrow construction of PDA is not important. What you require is this DCFL or not. In the exam, CFL is more important. DCFL you have very less questions. Okay, you are able to understand, you have a PDA, that absolutely fine. Okay, so ultimate goal is just to know which languages have PDAs, which languages we don't have PDAs. So tomorrow topic is very important, because we will talk about n number of languages, like we identified regulars, right? The same way we will identify CFLs. Okay, every problem that I take, I'll tell the logic in case if you don't know. So for tomorrow problem, for tomorrow this 20, how many? 27, right? Still we have so many. Here you can write variations. Okay, I'll give few more questions if you want. 27, right? You can also try some other problems. 28, A power m, B power n, C power k. What you can do is, I did m with n, m with k, right? Now you can try n with m or n with k. Okay, that means this one we are comparing with both, either this one or this one. 21. Now k we will try. K is equal to m or k is equal to n. Just for simplicity I am writing, but we don't actually construct like this. M equal to n we did, right? Now m greater than n or m greater than k. Still whether it is equal or greater than doesn't matter, right? The comparison is similar. So all these languages are not DCFLs only. What they are? Not DCFLs, but these are context free languages. So we have PDA, we have this 3 again. We have a PDA, we don't have DPDA for this 3. Okay, take this 3 also homework and understand why these languages are called as CFLs and why not DCFLs. Okay, yeah, thank you so much for today's session who are attending, and we have a very interesting session in the next class. But till now what we did is just for tomorrow session, because tomorrow session is more important than what is today and yesterday. Yesterday is to face PDA. Those people who face the PDA, tomorrow will become so easy. Okay, so easy because today and yesterday previous session was helping you to understand the next coming session. Okay, so summary is just we know now PDA and also DPDA. Now at this point of time, DPDA and PDA difference you could have understood. When you are not able to do with one transition, that means it is not a DPDA. But all the DPDAs, the relation is every DPDA that you did for the first 21 problems is a PDA, no doubt. But you don't need to design a PDA which is like a DPDA. PDA can be different from DPDA. PDA need not be, which may be DPDA, which may not be. Okay, it's very important. DPDA need not be DPDA. Even though you take deterministic language, I can design a PDA. which may not look like this one, right? So understand these 2 points, very very important points. Every DPDA you can call PDA, because the definition of DPDA always satisfies PDA, but PDA definition is non-determinism, that may not satisfy deterministic. Fine. So tomorrow's session we will try to understand the languages, why we call the languages CFLs and why we call DCFLs. Maybe I'll take 50 to 100 in between somewhere, but very very important session throughout all the 4 days. By that time, by tomorrow you will get to know what is CFL and what is DCFL. By this time we know how to construct PDA, right? Yeah, thank you so much for attending today's session, and I'm very sorry I'm not able to see anybody chat comment. That's why I'm not able to call anybody name now today. Thank you so much. Bye bye.